Okay, we're essentially done with the convergence tests. What I want to introduce to you today is a little concept that is, number one, maybe a shortcut to doing alternating series tests, but number two, has some implications if you go on in math and do some other things with Taylor series that are a little bit interesting here. Okay, so we have a series A sub n, and A sub n may have negative terms in it. It could be an alternating series. It may have a flipper, whatever. But if you're given a series, okay, here's a definition. If the absolute value, okay, of your sequence, in other words, if you take every term in your original series and make it positive, okay, if that series converges, then you say your original series converges absolutely, and therefore, by default, it also converges. Now, we got to be careful not to use absolutely in the traditional English sense of the word. Okay, when you say a series converges absolutely, you're saying that the absolute value of each of the terms makes a new series, and that series converges. Okay, that's what you're saying, and we'll show you why that's a big deal in a second. Now, if the absolute value of each term makes a new series, and that series diverges, but your original series converges, then you would say the series that you started with converges conditionally, okay, on condition, meaning not the absolute value of each term, that series converges, but the original series does converge. All right, now let me take you through two examples, and then we'll talk about why we care. Number one, I think you care because you don't always like the alternating series test, because it's got those three criteria to go through, and sometimes you don't like that. So this is maybe something you could go to as an alternative here. All right, so here's your first series. We're going to test and see if this is absolutely convergent or not. So what do? We've got to do the sum of the absolute value of the a sub n's, right? So that would be equal to sigma. Now, what does this absolute value thing do? Well, it takes all of your terms, makes them positive, so this flipper gets wiped out. Okay, so the series you now have is this series right here. Okay, 1 over n squared. Okay, and I should be writing my n equals 1 to infinities. But okay, now what do we know about 1 over n squared? Okay, I know that this is a p-series that converges. Okay, converges as a p-series with n greater, or with p greater than 1, right? So what does this mean? Okay, well, it means if I took every term in this series and made it positive, and that series converges, then obviously the series that has the negative terms is also going to converge. Okay, but as far as definitions go, okay, we would say that the original series we were presented with, okay, this one here, with the flipper, converges absolutely, which by default means it converges in general, okay? But when you say something converges absolutely, it's going to have some implications in a second here, okay? So that, for number one, is a way to avoid doing the alternating series test. Okay, you don't have to do the alternating series test now, because if your series converges absolutely, it's going to converge automatically. Now let's look at this one. Okay, if we're going to see if this converges absolutely, then we take the absolute value of the terms in our original series, which means I get the absolute, or I get sigma of 1 over n. Okay, and yes, n equals 1 to infinity. And what do we know about this series? This diverges, right? Diverges as the harmonic series. And so what does that mean about our original series? Okay, well, it means that I need to go now and see if it converges in general. And if it does, I can say this series converges conditionally, but not absolutely. Okay, so let's quickly go through the alternating series test, okay, AST, on my original series. All right, so number one, does the limit as n goes to infinity of 1 over n equals 0? Yes, it does. Number two, is 1 over n always going to be a positive number? Yes, okay, that's true as long as n is greater than 0, and n is greater than 0 because n starts at 1. That my terms get smaller as we go on down the chain, so I need to show that 1 over n is greater than 1 over n plus 1. Okay, and I'm going to show it working backwards. Okay, so I start with something that's true, which is 1 is more than 0, n plus 1 is more than n, and then I reciprocate and switch the signs so 1 over n is greater than 1 over n plus 1. Okay? So what does this mean? It means my original series converges. Okay? So converges by the alternating series test. And in general, okay, here's what we would say. Sigma -1 to the n over n, the alternating harmonic, okay, converges conditionally. It converges in general, but it does not converge absolutely. So we say converges conditionally. Okay, so it doesn't get you out of the alternating series test all the time. All right, first example got you out of the alternating series test. Second example does not get you out of the alternating series test. Okay, so you're asking yourself, what's the big deal between absolute convergence and conditional convergence? And it's a fair question, but here's the deal. Okay, if a series is absolutely convergent, then you may rearrange the terms and still obtain the same sum. However, it is possible to rearrange the terms in a conditionally convergent series and obtain any sum you wish. Now, that seems very bizarre, and I'll show you an example here in a second here. But think about this first thing that's said here. A series that converges absolutely, okay, if that's the case, you can rearrange the terms any way you want, and you don't affect the sum. There is a geometric series 1 minus x plus x squared, etc., that sums up to 1 over 1 plus x. From there, we integrated both sides to come up with a series for the natural log of 1 plus x. Okay, so we integrate the left, we get this. The constants of integration ended up being 0, but on the right side we get this series right here. And then when you plug in 1 for x, you get the natural log of 2 is equal to this series right here. Okay, the alternating harmonic series, right, which we just saw a second ago, right, here, right, the alternating harmonic converges conditionally, but does not converge absolutely. Okay, so what that means is you can rearrange these terms and get any sum you want. Here's one example that's going to blow your mind. Okay, blows my mind. All right, what did I do here? All right, I take 1 minus a half, right? So that's cool. Those guys are good. Then I put the minus 1/4 next. Then I group 1/3 minus 1/6. Okay, right here. All right, here's minus 1/8. That's down the road. Okay, and then I'm going to put 1/5 with 1/10 together. Okay, and this can continue forever. Now, what does this do? 1 minus a half gives you a half, minus a fourth, plus 1/3 minus 1/6. That's 2/6 minus 1/6. That's 1/6. Okay, minus 1 over 8, plus 2/10 minus 1/10. That's 1/10. Okay, and guess what? This pattern continues. Dot, dot, dot. And if I factor out a 1/2, look what you got. 1 minus 1/2 plus 1/3 minus 1/5. Sorry, 1/4 plus 1/5, etc. All right, that sum inside the parentheses is the same as the sum you started with, which was the natural log of 2. Okay, so now you have 1/2 the natural log of 2. Okay, so this is a big problem if you start with a number, ln2, rearrange the terms, and get a different answer, 1/2 ln2. Those aren't equal. Okay, and the reason they're not equal is because you're not allowed to rearrange the terms in a conditionally convergent series and be guaranteed the same result. All right, it's kind of a wild idea that you can actually create any sum you want by rearranging terms. All right, so that's kind of the bigger mathematical deal behind absolute convergence. Okay, but for us, it's mainly a shortcut to always doing the alternating series test. Maybe I can eyeball a series if I'm doing a multiple choice question, for example, and say, okay, I don't have to do AST here. I can just look and say that this is going to be an absolutely convergent because it's a P series, and that's going to be helpful at times.